Alright, welcome back everyone. So today we're going to be deriving something very special, and to see precisely why it's special, we are going to be examining the Galilean transformations. And specifically, we're going to be looking at why the Galilean transformations are incomplete when you start to consider ideas such as light speed moving between inertial frames of reference. And this gave rise to a lot of the very controversial ideas Einstein postulated, and gives rise to a lot of very, very profound and unintuitive phenomena from his special theory of relativity. And to reconcile some of these contradictions that you find in Galilean transformations, well, you have to add a different postulate. Because one of the first postulates that you have to consider between two inertial frames of reference is that the laws of physics are the same regardless of which inertial frame of reference you're examining. And Einstein needed to come around with an additional postulate to resolve some of these disputes. So when we get to that point, we will precisely see why it was needed to come up with a correction. So first, let's look at the Galilean formalism. First, I'm just going to write out ourselves a graph here. So we have ourselves two coordinate planes that we can use as relative inertial frames of reference that have some properties of motion occurring, let's say in this moving frame that is moving at some constant velocity v. And we have our stationary frame here that is denoted with these unprimed variable coordinates. So you can see those distinctions there. And then between both of them, there is a sphere of light that is expanding radially outward. And with that expanding sphere of light, you can presume that it is going to be equidistant in all directions. It may not look like a sphere, but this is just a representation of a quadrant to isolate a simplified version so we can construct ourselves a transformation sort of variable. Now, we're gonna keep this simple, so I don't have to keep saying the primed and the unprimed coordinates. It'll be easier if we just give them names. So for the unprimed stationary frame, we're gonna call this d-rock. D-rock. Points if you can guess that. Paul D-rock, maybe? All right, so d-rock in the unprimed frame, and then in the moving frame, we'll just call Einz. Call that Einz. Great. All right, so now we want to figure out how we can describe their positions relative to one another. Well, if we want to transform into, say, the moving frame and figure out what position he's at after some sort of displacement that he is moving with respect to time, well, then we can say that this displacement right here is just vt, and we can describe the coordinate transformation as such. So x prime equals x minus v times t. Now, you can see that pretty clearly because obviously his position is going to be beginning at some x position in d-rock's frame minus the displacement that he had been traveling in that positive x direction. So that'll give you your position in Einz's frame. Now, since we're not considering any rotational motion or any presence of a gravitational field due to the complications that would arise as a result, and to keep it as general as possible, we are going to say that y prime is just equal to y. And similarly, there is no visible z coordinate, but just to be consistent, z prime is equal to z. Those are going to be the same. Great. So now we are going to take one more assumption before we start performing some of these transformations. One assumption that you will see later on is an erroneous assumption. So the one, t prime equals t. The idea that when shifting between coordinates, time is absolute is the same in both inertial frames of reference. Now, you will see that this isn't exactly right, but to express the Galilean formalism, this is how we express it. So, next we want to figure out what physics remains the same between both frames. Well, how can we find an invariant quantity that gives us the same set of numbers, set of values, so long as we transform using these sort of transformations? Well, we should, if we were describing a sphere of light expanding radially outward, we could represent that with x squared plus y squared is equal to, well, just the radius here, and it's essentially just the Pythagorean theorem, but we can write that as ct squared. Okay, so let's just bring that over to the other side and just set it equal to 0. So we're going to do x squared plus y squared minus c squared t squared equals 0. Okay, so to preserve the laws of physics between both inertial frames of reference, if we were to transform from Einstein's frame using these transformation equations, we should end up with the same thing here. That is the idea, and that is what we need to preserve this idea of invariance. Now, let's write out our prime coordinates now for our radius of our sphere expanding. So we're going to have x prime squared plus y prime squared minus c squared t prime squared equals 0. Okay, so let's plug in our transformations, and what we should end up with is this. If we want to preserve this postulate of all physics being the same in inertial frames. So we're going to have x minus vt squared plus, well, y prime just becomes y. So y squared minus c squared, and then t prime just becomes t. So t squared equals 0. All right, foiling this out, we get x squared minus 2vtx plus v squared t squared plus y squared minus c squared t squared equals 0. All right, you can already see right off the bat there's something wrong with these cross terms, because we are clearly not ending up with what we need to end up with to preserve this invariance. So with that in mind, this is clearly problematic, these cross terms. Our assumptions of time here seem to be at direct odds with what we would otherwise expect to see in a moving frame relative to some light beam. So how do we reconcile these problems? Well, first we need to start out with some linear equations and some unknown variables and incorporate some of the fundamental postulates that Einstein came up with, in as well as what we already had postulated here. That is Einstein's two postulates for special relativity. The laws of physics are the same in all inertial frames of reference, and the speed of light is invariant and does not change between transformations. That needs to be preserved in order to uphold his theory, special theory of relativity. Okay, so let's look at some linear equations. And maybe you'd be asking yourself, why do they need to be linear? Well, that is because space is homogeneous. In other words, each and every point in space, at every variable point in space, the points between one another, as you increment throughout time, is equidistant apart. So because space is homogeneous, we can treat these transformations as linear transformations. So therefore, we can describe them using linear equations. So let's do that. We're going to have our linear equations here. All right, so first one, let's take the fact that we had assumed that t prime equals t. Well, that's clearly an assumption that we shouldn't have made. So let's construct ourselves a linear equation describing time now. So t prime, we'll say, is equal to a times t plus b times x. Okay, now let's write out our x prime, our position transformation equation, which we'll call x prime equals, we'll say, since c is pretty much already taken, let's just call it d instead of following that order. C is going to be needed. It's best we don't start mixing these up. So we're going to do d times t plus e times x. And as before, y prime is just equal to y. And same with z. Prime is equal to z. Now there is one place at which time will always be the same for both observers. That is when the origin points are coinciding with one another. So t prime is equal to t is when they are both equal to 0. So at time 0, they will agree on that. We know that for sure. So t prime is equal to t is equal to 0. All right, great. So now let's start figuring out and adding some scenarios. So let's say that Einstein, or rather, let's say that Dirac observes some physical event occurring at the origin. He looks at his origin and sees some physical event occurring and identifies that position as x prime is equal to 0. Okay, so if x prime is equal to 0, that must mean that if we plugged in 0 for that, then our x would be equal to vt. So x is equal to v times t. All right, so let's start plugging some of these in to our linear equation. So if x prime is equal to 0, we can plug that in over here, and we'll have ourselves 0 is equal to, since x prime is equal to 0, that would be dt plus e times x, which is just vt. So call e and then v times t. All right, so let's solve for d here. See what that gives us. So do d is equal to, well, if we were to move this all over, get rid of these t's, we would end up with minus e times b. All right, that is a little bit of information about one of our unknowns. Cool. So now let's analyze the converse sort of event. Say now we have Einstein observing Dirac's frame at the origin, looking at some physical event occurring at the origin, where, in other words, x is equal to 0. Okay, so if x is equal to 0, well, this time we need to flip our coordinate transformations by plugging that into the inverse of whatever this is, which would be, well, that would just be x equals x prime plus v t prime. And remember, x is equal to 0, so now we can solve for x prime, and we have our corresponding x prime variable, which is equal to minus v t prime. All right, so now what we can do is plug this back into our position transformation, and we get minus vt minus v times t prime, that's important, minus v times t prime is equal to, well, we got dt, okay, but we know x is equal to 0, so we can get rid of that term. So we're going to have dt, and let's solve for t prime here. So t prime will be equal to minus dt over v. Great. So now we can take this t prime variable and plug it into our linear equation for time. So if we do that, we'll end up with minus dt t over v is equal, well, remember, x is still equal to 0 here. That'll go away, and we'll just have at. Okay, so let's solve for d again, see what that gives us. So we're going to have d is equal to, well, we're going to cancel those t's out, so this is going to be minus a times v. Okay, great. We have narrowed down even further some of our unknown variables. So d is equal to minus e times v. D is also equal to minus a times v. So therefore, we're going to have minus a times v equals minus e times v. So if that is the case, that means that these relative coefficients a and e must be the same. So a is equal to e. So with that in mind, we can start reconstructing our new equations here. So just to ensure that we know when we're updating these, we're going to call this equation 1 and this equation 2, just so we can see how they're being updated. So for 1, we'll work on that in a second. So for 1, or 2 rather, x prime is, we'll just put this in terms of a. Put it in terms of a variable that you see in the time equation. So we can just narrow down and reduce the amount of unknowns that we have. Okay, so x prime, we'll say, is equal to d times t. Well, what is d? Well, d over here is minus a times v. So we're going to have minus av times t plus, and remember, we're just going to turn e into a since they're the same thing. So we'll call this a times x. So let's factor out this a, and we end up with x prime is equal to a times, well, rearranging this around, we just have x minus bt. All right, great. So this is updated now. So let's call this one 2.1. Okay? And let's update our time equation in terms of a by just trying to figure out a little bit of symmetry that we can exploit. So we'll call this 1.1, where we have t prime is equal to, well, remember, we want to exploit this symmetry to make it a little bit easier on the eyes. So pulling that a out, we're going to have a times t plus b over a plus b over a times x. All right, great. So now that we have that, what we can do is consider another event between both frames. Let's assume that Dirac and Einstein, in this particular set of constraints, Dirac sees a photon traveling along the x-axis, and Einstein sees the same thing. They both observe a photon traveling along the x-axis. And remember, the variable c, or the speed of light, will be invariant between both. So they should essentially see the same thing. So let's say from Dirac's frame, we have x equals c times t for that light beam. And then for Einstein's frame, we're going to have x prime equals c times t prime. So remember, you see how we have t and t prime to indicate our different frames, and x prime. But c, that doesn't get a prime variable. That will always be c. So now let's actually just start plugging some of these in, shall we? So let's plug it into our, let's say, this equation. So t prime, we'll say, is equal to, t prime is equal to a times t plus b over a, and x is just ct. So we're going to have ct, And now let's factor out one of these t's. So we're going to have that now becomes a times t with a 1 plus bc over a. And now we can pretty much just do the same thing with the position equation. So let's plug in x prime in for what we have here, and then we can also plug in our x variable in there as well. So let's do that. We're going to have ct prime is equal to a times ct minus bt. That is a t, by the way. Minus bt. There. All right, great. So now what we can do is factor out a ct here. So let's do ct prime equals, well, what do we have here on the outer side? Well, we just have cat. Sorry, Schrodinger. So cat, or cat, times 1 minus v over c. Now, the astute among you might already notice that there is some inherent symmetry, and that is perfect. That is exactly what we want. So what we can do is take this t prime variable and plug it in right here and start resolving some more unknowns. So what we're going to have is, this goes over here. Well, we're just going to have cat again. cat is equal to cat on this side. Oops, cat times 1 plus bc over a times 1 plus bc over a is equal to cat. Is equal to cat on this side, where we have 1 minus v over c. All right, so now we can cancel out our cats, and then we finally know the answer to the Schrodinger equation, because cat is dead. The radioactive atom has decayed. Cancel out these ones, and we just have bc over a equals minus vc. So we're going to have bc over a equals minus v over c. Now if we divide out this c, we just have b over a equals minus v over c squared. And there we have another unknown set of variables determined. Perfect. So let's update our equations again. So we have now, let's call this 1.2 here. So 1.2, and then this is going to be the same here. So 2.1 hasn't changed, right? So 1.2 we'll call t prime now equals a times t. Well, what did we figure out b over a was? That's just minus v over c squared. So t minus v times x over c squared. And we have x prime is equal to a times x minus bt. Those are the same. All right. We have finally narrowed down our equations to just one unknown variable a. Now, how shall we go about figuring out a now? Well, next we need to consider increments of time. We can represent our time equation like so. So we're going to call this delta t prime is equal to a times delta t minus v delta x over c squared. Here. All right, so now we can factor out this term t, delta t prime, and or delta t, not prime, and you will see why we did it. So we're going to have delta t prime equals a delta t, where we have now 1 minus, well, if we were to balance out this equation, we'd have to put a delta t in the denominator over here, which would mean delta x over delta t, which is just the velocity. So now we're going to have velocity squared over c squared. And this is one constraint. So this is telling us that Dirac is observing Einstein's clock to be scaled by a factor of a times 1 minus v squared over c squared. So we can effectively do the same thing from the reverse case. So if we were to do that, we would, in a sense, we would say that Einstein was looking at Dirac's clock from the origin, in other words, at x equals 0, which means that x prime is equal to v delta t prime, right? So his clock, x is equal to 0. Let's put that into our position equation. So we're going to have the reverse case, and sorry, this should be a minus, since if you recall, he is observed to be moving in the negative x direction. That's why we need that negative there. So since he's moving in the negative x direction, we can rewrite this as minus v delta t prime is equal to a times x. X is 0, so we're going to have a times x, or 0 minus v t. Okay, well, let's work this out and let's see what that gives us. Well, these v's are going to cancel, these minuses are going to cancel, and we'll end up with delta t prime is equal to a times, well, this should be a delta t here, so forgive me there. That should be delta t. All right, so if we were to put this in terms of delta t prime, well, we would just have delta t is equal to 1 over a times delta t prime. All right, so what was the point of that? Well, if you'll notice, there is some relative scaling factors when accounting for time between both inertial observers. So, as I mentioned before, from Einstein's frame, he is observing Dirac's clock to be scaled by a factor of a times 1 minus v over c squared. And conversely, we have Einstein observing, sorry, it's the other way around. We have Dirac observing Einstein's clock to be scaled by a factor of this. And Einstein observes Dirac's clock to be scaled by a factor of 1 over a. And from the essential postulates of relativity, these scaling factors must be the same. So, in other words, we're going to have 1 over a is equal to a times that. Is equal to a times 1 minus v squared over c squared. Now we can solve for a. Finally get our unknown variable solved. So we're going to have this moved over to the other side, move that over, and we're going to have a is equal to 1 over the square root of 1 minus v over c squared. And this right here shows up everywhere in special relativity. This is a special term known as the gamma factor. And the gamma factor is denoted with gamma, which is equal to 1 over square root of 1 minus v over c squared. Now, this is the scaling factor that we need to resolve our dispute that we had before, where this exclamation point was. Once you incorporate this new scaling factor, this is all solved. But this also leads to some very, very stunning results. So if we were to update our equations, we would have 1.3 and 2.2 now. We're going to have t prime is equal to gamma times t minus v times x over c squared. and then x prime is equal to gamma times x minus vt. And there we go. These are what's known as the Lorentz transformations, the updated versions of the Galilean transformations. And I will leave it to the viewer to try to do exactly what we did before at the start of this video to see that everything cancels out and you will end up with this invariant quantity. In other words, this is what's known as the space-time interval, and it's what all observers can agree upon. So now we have our updated Lorentz transformations, and these should come as quite a bit of a shock to you, especially after what we just saw when relating the scaling factor in terms of time. If you were to relate the scaling factor in terms of time, represented by this gamma factor, well, you would see that the moving frame, t prime, is just equal to, well, it would just be the moving frame multiplied by a, which is what we know to be gamma. So therefore, what we can do is represent it like so. Gamma times our notion of time. And this variable t is known as the rest frame. Now this represents our moving frame, and if we were to look at it a little more qualitatively, we would have t prime equals t over the square root of 1 minus v over c squared. So v squared over c squared. If you see here, numbers, this value right here, it's going to be very small. It's going to be very small. And as this number, we'll say that v is much smaller than c, well, this just ends up as a very small number, and you're not going to have a very noticeable difference. But if you're moving at speeds almost equal to c, say v is equal to c, if v was equal to c, you would notice that this ends up becoming 0 in the denominator. So as v approaches c, t prime approaches infinity. So with faster and faster speeds, this time is going to be expanded. It's going to be dilated. Clock in this frame is going to tick slower than the clock in the rest frame. And that is just one demonstration of time dilation. I hope that gives you a little bit of intuition as to what's actually happening between two inertial frames of reference. And I will maybe do a little bit more of a qualitative explanation why time dilation is approachable, and it actually is something that we use in everyday life. So with that in mind, I hope you enjoyed it. Thanks for watching.